The Greeks are defined as the sensitivities of the option price to a single unit change in given underlying parameters or pricing variables. They represent the different dimensions of risk of an option. Why are they important? Firstly, they are used by traders to estimate how a change in market conditions will affect the value of the option positions. And secondly, they are used as hedging metrics such that each component risk may be treated in isolation and hedged accordingly to achieve a desired exposure. The delta of an option indicates the change in an option's price for one unit change in the price of the underlying asset. Delta is dynamic and changes according to movements in the underlying instrument, and as such is frequently used as a measure to establish the correct hedge ratio or parameters. Gamma measures the rate of change in the delta with respect to changes in the underlying price and is important because it estimates the extent of the convexity in the option price. When establishing an effective delta hedged portfolio, a trader may also seek to neutralize the gamma exposure such that the hedge will be more robust over a wider range of underlying price movements. Vega, although not actually a Greek letter, is a measure of the impact of changes in implied volatility on the option price. Vega indicates by how many units the option price will change, given a 1 percentage point change in the expected volatility of the underlying instrument. Theta measures how much an option price will change due to the passage of time and gives an indication of the decay characteristics of an option. Rho measures sensitivity to the appropriate interest rate. Rho, along with mu, the dividend sensitivity, are the least used of the primary Greek since, except under extreme circumstances, their effects on option valuation are the least sensitive. Let us now explore these risk measures in more detail. There are three common uses of delta. First, the measure of option sensitivity. Second, delta is a gauge of the probability of exercise. And third, as already discussed, delta is a hedge ratio for creating a riskless portfolio. Deltas are commonly quoted as a percentage of the total exposure, for example the number of shares represented by an option contract, and will be a number between 0 and 1 for a call and 0 and -1 for a put. As can be observed above, for deep out-of-the-money call options the delta will be close to 0. A small change in the stock price has little impact on the value of the option. For deep in-the-money options, the delta will be close to 1, since a small change in the asset price will have an almost 1-for-1 change in the option price. Similarly, for deep in-the-money puts, the value of delta will be close to -1, while the delta for out-of-the-money puts will be close to 0. Delta is always positive for long calls and short puts, and negative for long puts and short calls. Why is this? By way of an example, the delta of a call option is always positive because a call becomes less out of the money or more in the money and hence more valuable as the asset price increases. Conversely, the delta of a put option is always negative because a put becomes less in the money or more out of the money and hence less valuable as the asset price increases. Delta is dynamic. As a spot price moves, delta changes and also becomes more sensitive as expiration approaches. This means that a hedged portfolio will need to be dynamically rebalanced to keep up with the gamma risk, the fact that delta changes. To hedge a portfolio of option positions on the same underlying asset simply takes the sum of the deltas for each individual position. Since the delta of underlying asset is always 1, the portfolio could be delta hedged, buying or shorting the underlying in the cash markets to the value indicated by the total delta. How can we use delta to position a portfolio? Bullish investors want to achieve a positive position delta, while bearish speculators want a negative position delta. Gamma can be described as the rate of change of delta. The greater the gamma, the greater the reaction of the delta to price changes in the underlying instrument. Gamma can thus be used to recalculate delta. It is the required adjustment for the fact that option prices do not have a linear relationship with the spot price, and that delta provides only a linear approximation of the change in the value of an option that becomes less accurate the larger the change in the underlying asset price is. The resulting hedge error is from the difference between the estimate initially derived from delta and the actual relationship. So, how can we use gamma? Gamma has two main uses. Firstly, as a measure of the accuracy of the delta ratio. Secondly, as a gauge for determining how frequently a delta hedge position needs to be rebalanced. Understanding gamma will help you determine how much the delta of your position will change and alert you to how frequently you must adjust your hedge ratios. What observations can we draw? Gamma is always positive for long positions in plain vanilla options and negative for short positions. Also, it is the same for both calls and puts, with the same strike and time to expiration. If a portfolio is positive gamma, then the increase in the value of the portfolio for a given increase in the price of the underlying stock will be greater than the predicted by the static delta. A positive gamma position means that the option holder effectively becomes more exposed or longer to the market as it goes up and less exposed or shorter as the market goes down, which is clearly good news in both cases. A positive gamma position implies that the position value is convex with regard to the underlying asset. Negative gamma positions exhibit the opposite effects. If gamma is small, it implies that delta changes slowly, which implies the cost to adjust the portfolio will be small. If gamma is large, it implies that delta changes quickly, and the cost to keep a portfolio delta neutral will be large. Gamma increases as both the time to expiration and the stock volatility decrease, and as the option gets near the money. For an option that is near the money, gamma increases as expiration approaches. The large gamma spike, often referred to as pin risk, as indicated in the graph, reflects the heightened sensitivity of delta to spot moves. The gamma risk for deep in the money and out of the money options falls dramatically as expiration becomes very close. Vega tells us how much the option premium is going to change for every percentage point increase in implied volatility. Volatility changes are critical because of the major impact that they have on option valuation. Vega is always positive for conventional options. Why? Because every option increases in value as volatility increases. It is a question of whether you are long or short the option that determines whether you are Vega positive or negative. It should also be noted that Vega is the same for both calls and puts with the same strike price and time to expiration. What else can we say? At the money options have the largest Vega and therefore are most sensitive to changes in the implied volatility. Regardless of whether the option is a call or a put, an option with the same characteristics will have equal Vega exposure. Also, Vega generally increases with time to expiry. The more time remaining to option expiration, the higher the Vega. This makes sense as time value makes up a larger proportion of the premium for longer-term options, and it is this time value that is sensitive to changes in volatility. As volatility increases, gamma generally decreases and vice versa. For options that are both close to expiry and at the money, a significant change in volatility is likely to impact considerably on the intrinsic value of the option. At this point, delta becomes more of an issue. Theta measures the sensitivity of the option price to changes in time, and convention dictates that we measure time in days. As the time remaining to expiration nears, theta exposure becomes increasingly important since the speed of decay accelerates rapidly. As a rule of thumb, an option will lose 1/3 of its value during the first half of its life and 2/3 during the second half of its life. Why is this so? because there's less probability of a positive intrinsic event. Thus, if you are long an option, you are short theta, regardless of whether it is a call or a put. The option will lose value with the passage of time, unless there is enough volatility to offset the decay. Conversely, if time decay works against an option holder, then it stands to reason that it must be working in favor for option writers. Indeed, theta is positive for option writers. Options that are far from expiration have a low theta because there's plenty of time for the spot price to travel in the direction of intrinsic value. Theta peaks for at-the-money options because the potential for intrinsic value to begin to rise is the greatest at this point. As the option gets further in the money or out of the money, this characteristic changes. Time decay, depending how far away from the money, will actually decelerate into expiry as shown in the graph. Another important relationship to consider here is how theta behaves with regard to the absolute level of volatility of the underlying asset. Higher volatility means greater time value. Thus, there's more time value to decay. Note also that theta is interrelated to gamma. If a portfolio is short gamma, i.e. short optionality, any time decay, all else remaining equal, benefits the book, as the option can be bought back at a lower price through the passage of time. Indeed, by linking the Greeks, we can establish an additional general relationship that exists between theta, gamma, and Vega.